I'm happy to share this third session by Jim. So Jim, please go ahead and if you have questions, please ask me to talk in the microphone. Then the questions can be registered too.
Yes, I'm almost there. Yes, I'm now, the little camera will follow me as I go around. It's very cool. And I'm not sure it can keep up because I tend to go back and forth and back. Anyway, so I'm told. I don't realize it myself. Thank you for coming again. Next week, people will really start getting tired, and you have really interesting people coming, and I hope you make sure you stay awake for Xiaoming and the others. Tomorrow, I'm going to provide Stephen and Danilo's analysis of a universal scaling function for a rigidity transition. Today, I'm going to explain why the things that this scaling function predicts are useful. And what it predicts is the linear response. And the linear response is just what we all make fun of. Like, glasses have all these interesting avalanches and things, and why should I care about linear response? Okay? So I'm going to tell you a little bit about linear response and things like that, which is something that Tom Lubensky just went through at lightning speed. So you will recognize a few of the symbols that I tried to use as standard, and I was guided by Danilo and Stephen to write down dynamical matrices and things, which I didn't really know what they were before we started. But the job today is to tell you a little bit about what will happen on Friday. So you've heard Pierfrancesco Urbani tell us about jamming. Jamming, you have these soft spheres that when they overlap, they complain, but when they're not overlapping, they're happy, and they go from a state where they don't overlap because there's lots of room, and you squeeze them, and at this isostatic point, which I won't talk about much at all today, they become elastic. They become a solid. And they become a very complicated solid, that if you shear it, you get a bulk modulus and a shear modulus, but if you shear it very much, you get avalanches. And on the liquid side, on the fluid side, they have very complicated motion. When they're really dilute, it's not a complicated motion. But when they're all getting crowded, you get pictures like the right-hand side here, where a simple shear this way and this way, I'm not sure if that was what the experiment did, but I'm guessing produces very complicated motions with some particles swirling and some particles swirling in the wrong direction and on short length scales. It acts like a fluid on very long length scales. There's a diverging length scale at which and frequency scale at which it begins to look normal. And similarly, in the jam state, there will be avalanches that have complicated fractal behaviors and long-range pieces, and all those studies that I've been telling you about for the last 2 days are going to be ignored in the next 2 days. Okay? And the model that we'll be studying is a mean field theory. And I tried to argue that mean field theories work above the upper critical dimension, and all the predictions of Pier Francesco Urbani's, I'm practicing so that I can say the whole name without, am I pronouncing it correctly? Yeah. Pier Francesco, good. For a while, yeah. You can imagine if I taught 50 people, or like you, if I remember 2 of your names, it'll be a miracle. Ben, Felipe. Felipe, meet Danilo. Both of them want to meet you at some point, and Danilo might actually be from the same part of Brazil. Anyway, where was I? Yes. There's another rigidity. I'm going to talk about rigidity transitions using this mean field theory. There's another rigidity transition that we will be talking about, which is called rigidity percolation. You'd start with a network of random or maybe a crystalline network, and you dilute it. And you dilute it for a while, and it stays rigid. And you dilute it even more, and it becomes floppy. You may have heard of percolation. That's where it turns to dust. It breaks up into little pieces, and of course it can't support a shear. But if the bonds in this network are only connecting, are only springs, then you saw the mechanisms that Tom was talking about in the early parts of his talk before he flooded you with equations. Those mechanisms, they're regions that can flop around, and at some point it all becomes floppy. If you try to push on the 2 ends, it just collapses. It just moves. Okay? And that rigidity percolation has been studied for far longer than jamming, and it's not the same. In fact, it seems to be different for every possible lattice. I'm going to ignore that. I'm going to pretend that an isotropic rigidity percolation is a unique thing, and we can describe it with our theory. Maybe it's true. Danilo tells me, yes, it's of course true. And, but what Danilo and Xiaoming Mao, who talks next week, and Olaf Stenold and Tom Lubensky, who you've been hearing, they have this great calculation where they look at a mean field theory for this transition on this rather complicated lattice, which I'll talk about more. It's got hexagons, and it's got triangles, and it's got nearest neighbors, and all kinds of things. And they found something. First of all, they found a rigidity percolation, and they found a different thing that looked like jamming. I'm not going to talk about that today. That's for, or I might talk about it later if I'm too fast. So slow me down, ask me lots of questions. But rigidity percolation, one of the things that makes it different is here, as soon as these particles touch, if you have harmonic springs, which is a technical detail, the bulk modulus suddenly jumps. The bulk modulus behaves differently from the shear modulus. The shear modulus is just barely, just grows linearly as you make the particles have more contacts as they start overlapping. And the bulk modulus jumps. Rigidity percolation, typically both the bulk modulus and the shear modulus disappear at the same time, and they disappear continuously. And we will have, in this scaling picture, which we build upon this calculation, we'll have a scaling picture that that this is an unstable fixed point and there's a crossover function to this, which is why I talked about crossover functions earlier. So that's a preview of tomorrow. Good. So what the original paper with Xiaoming and Tom Lubinsky and Danilo did was to just calculate one thing. They calculated effective frequency-dependent elastic constants. Or you could think of it in the floppy side as frequency-dependent viscosities. Okay? And that's a kind of a weird thing to think about. And you say, well, why do I care about a frequency-dependent elastic modulus? And the claim I'm going to make, and the foundations of the first two of our papers that Danilo headed off, is that knowing the frequency-dependent elastic modulus tells you a whole lot of useful things. So if I were to write down a theory that's useful for experiments for crystals and liquids and gases, for crystals and liquids, we very rarely, for crystals, we very rarely, rigid things, you very rarely care about anything other than linear response. If you have a piece of iron or a piece of silicon, you'll have linear response, you'll shear it by a fraction of a %, and then after that, you either break or you mush in some horribly complicated way. Almost everything you care about for solids is linear response. Fluids, I admit, you have turbulence. And gases, you know, you've got Boyle's law, you know, you can squeeze it quite a bit, but for materials, linear response is 99% of the physics probes. Some engineers will care about, you know, things breaking, and there's a lot of attention to that. But even the fracture people, they will do linear response for everything except right near the crack tip, and they'll call that the nonlinear zone, and they'll ignore that. Or they'll spend a lot of time making effective theories for the nonlinear zone. Anyway, so knowing linear response isn't just the elastic moduli. It's the whole technology, which if you have seen it, you'll recognize a few of the things I say, but it's a giant machine. In my course, I have a chapter on this, and this is the part where knowing complex analysis and knowing and you can just sit there and do formulas and make progress as opposed to anyway. So linear response will tell you all those scattering, X-rays, neutron, acoustic scattering, inelastic X-rays see phonons, elastic X-rays tell you the crystal structure, tell you about defects, neutron scattering, acoustic attenuation, anything about dissipation, the viscosities, pulse probe experiments where you hit it in one way and you measure how it responds. You excite electrons across the band gap and look at the effects on the elastic constants. All kinds of things are all done using linear response theory. In fact, I would say this happens a lot in physics. That when I was an undergrad, I learned group representation theory, and I thought this was a great theoretical triumph. And as I go around, the only people that really know group representation theory are experimentalists. That it's taken from, you know, some abstract thought to practical tool. If you have a defect in a crystal, you have to know the group representations to figure out what the mode is and A3G and all this. And my colleague Al Sievers was the one who knew all that stuff, who will talk about it like the old friend. Linear response theory is like that. The experimentalists know this a lot better than the theorists. It's useful to them on a day-to-day life. To us, it's, okay, I've got the frequency-dependent elastic moduli. What else do you want? And they say, well, you need all these predictions, and so you have to learn that stuff to make those predictions. I'm teasing, but sort of. Now, these days, we have numerical experiments, but nobody studies these things for jamming, it seems, and we're trying to change that. Okay, so what are the key things? There's a correlation function. I'm not going to tell you about correlation functions. That's a good couple of lectures, or a really nice exercise where we talk about correlations of people on subway cars, but we're not going to do that tonight. This tells you if you're, there's how things evolve. If you start not in the equilibrium state of the crystal, or solid or liquid, but perturbing away, how will it evolve in time? This is the dynamics. This is the equation of motion, in a sense, hidden inside this function, where you can start in an irregular spot as a function of position. There's some weird initial state. There's a susceptibility. This is how things move when you kick them. If you hit a force on these atoms, you Fourier transform the force, and this will tell you how it rings later on if you Fourier transform in time. And then the susceptibility has a real and imaginary part, which are famous quantities that have this rather unilluminating name, psi prime and psi double prime. And the real part gives you the in-phase response, like an elastic modulus. And the imaginary part gives you the out-of-phase response, which, if you haven't seen it, the out-of-phase response tells you how much energy is dissipated per cycle. So I would claim all of these are somehow intricately related to every other one. And if you can calculate one of them, you can calculate all of them. And if you can calculate the frequency-dependent elastic moduli, at least within this context, I'll talk about this in a moment, maybe you can calculate everything. In fact, we do calculate everything in our model. So a bunch of relations, the Onsagar regression hypothesis, that if you know the correlation function at t equals 0, deviation from equilibrium, you multiply by the Green's function, and you get the correlation at a later time. Who would have thought that those two were connected? The susceptibility, well, I just told you, it's the real part and imaginary part. The power dissipated, if you know how it responds to kicks as a function of time, you Fourier transform, you take the imaginary part, and that tells you how much energy will be dissipated if you give a frequency-dependent force on the object. And I think I could have done this psi of k and omega, except that I just, anyway. Then there's a fluctuation dissipation theorem that connects the susceptibility to the time derivative of the correlation function. And then there are these really bizarre Kramers-Kronig relations that connect the real part and the imaginary part of the susceptibility through these integrals that follows from Cauchy's theorem, that follows from causality. So someday, if you haven't already, you should look at this, especially if you're an experimentalist. So all of those relations work for anything that's sort of described by, as a material, magnets and superfluids and everything. Here, we're interested, our title of our school is disordered elastic materials. And what I'm thinking of as an elastic material is something that has a response when you deform it, when you move stuff from x to x plus u of x. And Tom's already gone through this. And the whole idea for us is what happens at small wave vectors at long wavelengths and small omega at long times. Why do we care about long distances and long times? First of all, when you get down to the atoms, things get complicated. For us, things get complicated on much longer length scales, all those funny swirls. And what we're interested in here is saying, if I've got this hunk of glass, and I hit on it, and it goes gong, how do I understand those sound waves? You don't care about all the complicated non-affine deformations on short length scales. All you care about is that sound wave and how quickly it'll go away with, because it's scattering off of all those little things, and it's losing energy to all those other modes. So one of the things we're going to do is we're going to write a theory that has dissipation even though there's no friction. We're going to start with a model with harmonic springs and no friction, and we will end up with something that looks like it has friction for the same reason that real solids have friction. The energy is conserved. In a real solid, you hit that bell with a hammer, it goes gong. It doesn't vibrate forever. It slows down and warms up. All that energy gets turned into heat. But heat, and that process you can think of as there's some kind of long wavelength plane wave going through this material, and for one reason or another, some of its energy gets scattered into other wavelengths, and which you're not paying attention to, typically short distance wavelengths. And that scattering is just the sneaky thing that the kind of mean field theory that Danilo used with the original paper allows you to calculate. So we're going to take a gradient expansion, and so you could think of and then you use various symmetries to simplify it. So if you take a material and you ask what is its what parts of its behavior do I have to care about? I can't have anything that I care about that just depends on you. What do you mean, just depends on you? That's the only thing you have. Well, I'm saying it can't just depend on you at one spot. It can depend on differences of you, but because there's a translation invariance, because you can just move the whole material to the left and it's going to look the same, all your equations of motion will have to depend upon differences of you, which, because we're assuming long wavelengths, only the first derivative is going to be the important one. Tom would say, well, if you do large rotations, then the second derivative, square the first, never mind. Okay, only the first derivative is going to be important. That's even true for Tom. It's sometimes the second derivative is important for topological modes, but never mind. Xiaoming will tell you about that maybe. It also, we're going to assume rotation. I mean, even in a crystal, even in a weird crystal, if you rotate the whole crystal, it's the same. And so you know that an overall rotation can't matter, and that means it's not just the gradient of this displacement, but it's this shear that matters, where here I have dropped another term that's important for large rotations, but this is the linear shear. Remember, I'm doing linear response, so I'm allowed to cheat. Yeah. Then I can write down the dynamical matrix, which takes this shear and writes the change in energy to quadratic order. When Tom derived this, he actually went through all the details. I'm just going to write it down. And then, now notice this isn't quite the dynamical matrix, but if I set the density to 1 and all the masses to 1, then it's the dynamical matrix. It's really, yeah. Then I'm going to assume we're going to be focusing on homogeneous isotropic materials. Homogeneous, everyone seems to care about, except, of course, when you add the disorder, it becomes microscopically inhomogeneous. But on long wavelengths, you believe that's self-averaging, and you look at things and they're kind of self-averaging. And this piece of glass and this part of the glass, it really behaves the same when you hit it with a hammer. And so you have an elastic energy that you can write in terms of the Lamé constants. I remember the name, but I don't know which one. This one's the shear modulus, and I think we all call this one lambda. And in Q space, Fourier transforming U of x, this is the matrix that comes out. Okay, so lambda plus 2 mu and mu should be familiar to you. And I'll be talking about them like old friends. And the fact that you may have seen them for the first time in Tom's talk, by now you should say, oh yeah, I remember that. Okay, bulk modulus and shear modulus are things that you'll hear a lot about. They're just linear combinations of lambda and mu. Okay? Then there's the dynamics. This is the sort of energy part. For long wavelengths, I can take the complicated energy that depends upon exactly where all the bonds are and reduce it to something that only involves gradients. Here, I have to figure out what the dynamics is. And so if energy is conserved, if I have spring lattices kind of thing, then the Green's function, which embodies all the dynamics, you can write down. You basically write down Newton. I think this is true. You write down Newton's equations, and then you Fourier transform, and whatever your dynamical matrix is, you get a minus omega squared inverse. Okay? So this is a matrix, and this is the identity matrix that I write as a 1. And at low frequencies, in fact, I think at all frequencies this is technically correct, but we're going to be interested in very low frequencies. If energy is not conserved, if, for example, you're moving and you have each sphere or each atom or each whatever is damped proportional to its velocity, which is what it would be if it was all alone falling in maple syrup. Sorry, you don't know what maple syrup is. Thick goo. It falls proportional at a rate proportional to the force on it. The resistance is proportional to the velocity by a constant, which is the coefficient of damping, gamma. And this is the formula. Now, of course, real materials have viscoelastic properties, or elastoplastic, sometimes it's called. And this function can be arbitrarily complicated in terms of omega and stuff. But we're doing low frequencies. This took me a long time to figure out. And Danilo and Steve will tell you about all these emails. I said, what's going on? How can I do it? But if energy is conserved, this has got to be it. If you have viscous damping, this is going to dominate at low frequencies because omega is much bigger than omega squared at low frequencies. Now, that's not the end. It's kind of artificial to have a particle in goo unless you're a colloid scientist. So Ittai Cohen, is Ittai here? There he is. Ittai Cohen, our other co-organizer. Meet Ittai Cohen. He helped organize this whole conference, along with Danilo and Carolina. There they actually have goo that they move. In fact, they build their system with goo instead of water for reasons that are important. I don't remember why. But actually, even goo the stirring around of one sphere will change the interactions with other spheres, and you can put that into this dynamical matrix. It's maybe pretty complicated. You can also think of dynamical matrices where in between the springs they have damping. And that gives Kelvin damping and Maxwell damping. And that gives you other formulas that you could, in principle, have here. So if you have momentum conserved, but energy is not conserved, there's yet another formula. Okay? But if you're willing to say I'm doing only very low frequencies, like elastic theory, you can simplify the problem. You can have a few different cases for how the lowest frequencies damp. Okay. So this original paper calculated the universal scaling properties, say, of the bulk modulus, curly B. This is the universal scaling function for the bulk modulus, and this is the critical exponent as you get close to the critical point. And it looks like it's derived from something else, but really they calculated this and they used it to derive all the other stuff. Okay, so this table is telling you how to calculate the bulk modulus, the shear, the viscosity, and the correlation function in Q space, which is called S for some reason, in terms of critical exponents in universal scaling functions. So here is curly L, which is one particular susceptibility. It's a kind of a peculiar susceptibility, and I think we used it because we were writing another paper where we were pretending we could understand strange metals involved in high-temperature superconductors as an electron jamming problem, except it was actually an electron rigidity percolation problem, and the experiment was measuring this longitudinal susceptibility. Did I get that right? Longitudinal susceptibility?
Yeah, it's correct. Yeah.
Oh, good. Oh, good. And this longitudinal susceptibility we deduced from Liarte, Steno, Mao, and Lubinsky's work had a power law and a universal scaling function of this form. Call this capital Q, call this capital omega, and call this capital W, where if there's no damping, in that particular case, nu was 1, z here was 1, phi here was 1, and I've forgotten what, I didn't write down what gamma was, whatever. And this curly L, they got an explicit formula. Okay? This was a remarkable calculation that's in the appendix or the supplemental material, I've forgotten. No, not this formula. This formula was derived from the corresponding formula for the bulk and shear modulus. Okay? And if you know this, you can use these sneaky formulas relating everything to everything else to compute the original bulk modulus, the viscosity, the correlation functions, and all that. All right.
Jim, a quick comment. I think there is a typo, but it's nu is 1/2, and for no damping, I think z is 2, but never mind.
Oh,
It's just
okay.
yeah.
Okay. Remind me, and I'll fix it just in case I ever give this lecture again. But I should have it right. Yeah.
And then, okay. Steve is telling me that.
I have the jamming number or I have the rigidity percolation number.
Oh, okay, never mind. Thank you.
But I guess okay, maybe I
that's
wanted
fine,
the jamming number. Maybe I wanted the jam. Who knows? Okay. Okay. So, So this is giving you motivation to listen to an entire hour-and-a-half discussion of deriving the effective lasting moduli. Okay, with them you can do everything. Okay, so an example of using this table, if I wanted the correlation function, it would have the form delta RP to this power y times this universal scaling function, which I get by taking the imaginary part of P. Nuts. I don't have P in my table. I must have goofed. Okay.
P is the universal scaling function. That's the density. It's not in your table.
It's not in my table. Okay, nuts. I thought I copied the table. Never mind. None of you care, right? Okay. But getting the wrong exponents is just feeble, and leaving out anyway. Yeah, good. The reason that I bugged these two for several days before I finally figured out Green's functions is that it wasn't obvious to me, and it's still, I'm insecure that you can really describe arbitrary elastic solids just with a frequency-dependent modulus. So for example, whatever happened to the wave vector, Q? There's a wave vector there. And you want things, you know, all the chi's, all those things are a function of Q and omega, and we're describing it just in terms of the frequency. And maybe it works, and it kind of hangs together, But you know, everything I know about linear response, I learned to write the chapter of my book, and I learned from these two guys, and I'd really like to get somebody who's got more background, who's been thinking about glasses, all the replica theory calculations. Can they really, all their predictions for macroscopic behavior, can they really be embodied in two elastic moduli in all dimensions? Never mind. Okay. So it seems possible that any uniform isotropic elastic medium, already uniform isotropic elastic medium, must be describable using frequency-dependent elastic moduli. I don't know that that's not true. Doesn't mean it's true. And I'm clearly making assumptions that there are no long-term memories in the material, and there are no, that it's in a stationary state. And you know, real glasses have aging and things like that, but they age so slowly, they're well approximated by the sort of instantaneous behavior, and maybe all of that can be described by a frequency-dependent modulus. Could be. So that would mean if you have a frequency-dependent modulus and you stick it into the dynamical matrix like this, that could describe glasses, gels, forms, and sand piles, which on short length scales and high frequencies do very complicated things, but the fact that you don't see those complicated things on long wavelengths, the fact that it seems to be flowing to the universal fixed point of elastic, homogeneous isotropic elastic, which is not trivial, but appears to be true, maybe we can just calculate these two constants. And our job as physicists is to do these two or something equivalent. That would be an immense simplification to some, in some ways. Now, let me be clear. Just because all you have to do is calculate these two things doesn't make our calculation the right one. In particular, it's certainly not right for real glass. Just because there is a continuum theory doesn't mean that it's a mean field theory. The three-dimensional Ising model has linear response. You can write down linear response theories for every place except right at the critical point. That doesn't mean that mean field theory describes the three-dimensional Ising model near the critical point. But we have hope because all the predictions that they do in infinite dimensions seem to work in 3 dimensions and 2 dimensions. I'm going to argue they really work in 3 dimensions, and in 2 dimensions they work. I won't argue today because we're not quite done with the 2-dimensional calculation, but there seem to be logarithmic corrections in 2 dimensions. And we're excited by the fact that our calculation, even though it's mean field theory, seems to show log corrections to scaling. But that's, anyway. If the upper critical dimension is 2, then certainly in 3 dimensions and mostly in 2 dimensions, you should believe that a mean field theory like ours might work. So I believe very briefly, Pier Francesco Urbani told us that there was a theory called mode coupling that worked, far away from the glass transition, and that was a great step forward for spin glasses where you could prove it rigorously happened, and that made the cages. But then there was the Gardner transition, and then there's jamming way down at the bottom. And our theory, which is not for infinite dimensions, looks very similar to mode coupling theory. And I made fun of mode coupling theory for years. I was their enemy. And I should just, it's always good to say I was wrong. And I'm not sure that all of my arguments was wrong, and I was really focused on other things, but I thought a self-consistent theory that made things go rigid just because everything around them was getting thick, so they got thick, and then self-consistently everything would freeze, seemed too simple, and now we're doing it. Good. So our calculation makes sense because it looks like the upper critical dimension is 2. That's to say there are fluctuations on all scales. There are avalanches in jam systems, but they're too weak to change the mean field behavior. If the local fluctuations are so evil that every sample is different from every other one, then there's no continuum theory even in the phases. So fracture is like that. I was telling you, you pull that beam that you're testing to build a bridge, you pull it once, you pull it a second time, another identical beam as far as you're concerned, they break at all different rates. They're not self-averaging. Fracture is not self-averaging. But glasses, for their linear behavior, do seem to be self-averaging. Doesn't mean that the glass transition is described. Now, I don't want you to be left with the idea that whenever anybody says the glass transition is well described by jamming, that they're disagreeing with me. What I'm saying is very close to the jamming transition, we definitely don't agree with real glasses. So, for example, our theory, the bulk modulus and lambda jump. And the shear modulus goes to 0 continuously. What about glass? Anybody know how the bulk modulus changes at the glass transition? Does it jump to 0? Is a liquid glass got no bulk modulus? You're saying, what do you mean? It's a liquid. You can't squeeze a liquid. It's not like it's a 0 bulk modulus. And you know, the atoms in a liquid aren't floating and not touching one another. It's really strange to think of that as the other side. More specifically, like mode coupling, we have a viscosity that grows as a power law. Real glasses, there are immense numbers of experiments and controversies, but they basically follow something like a Vogel-Fulcher law, which exponentially grows as you approach a temperature which is well below what we would call the glass transition temperature, but that's where it freezes out of equilibrium. It's sometimes called the Kautzmann temperature, but whatever, it looks like this, which is much different from a power law. It grows much more severely. And I already apologized for complaining about mode coupling theory for all those years, yeah. Yep.
In your notation,
Say again?
what does it mean P is pressure? P the scaling, yeah.
Oh, P is going to be the probability of removing a bond.
Okay.
And you're right. It's kind of strange to introduce that in a part of the talk where I've not yet introduced the model where I remove bonds. So we have, in fact, two different P's. There's removing this kind of bond and removing that kind of bond, which will then replace by, this is the P that describes how much of the lambda I've removed, and I'm going to punch holes in systems and remove lambdas in one set of holes and mu's in the other set of holes, and that'll be entertaining. Okay. Now, why does everybody say jamming is describing real glasses? It's always in the list. Oh, it describes foams, it describes granular materials, and it describes many properties of real glasses. And it does. And it's natural. We're always making approximations to nature to drive our theories. And those approximations give you behavior that is comprehensible. Jamming is a comprehensible theory of glasses, but it needs to be corrected. And it can be a good theory of glasses except near the critical point. Mean field theories often work that way. And even though there's a critical point in real glasses, if you believe that, not everyone believes in the Vogel-Fulcher-Kautzmann temperature. And the way you see that is you see a property that's otherwise mysterious that's explained by this nearby critical point. And you can even make a little theory. You can say, well, here I have a critical point, and I've got a relevant direction, and that relevant direction is not too big, so I can still see the behavior as if. So if I have a magnet, right, which has a critical exponent beta and stops being magnetized, but I've got a universe in which there's always a magnetic field, external field, then I will see something that looks like it's going to go to 0 with a power law, and then will be a little rounded. And that's a way of thinking. I'm not sure everyone in the field believes this, but it's a way of thinking about real glasses. The real glasses are different because they have attractive interactions between atoms. That's what makes it not a gas, but a liquid. A liquid is a gas with enough attraction that all the atoms, most of the atoms come together in a big blob and move around, right? And maybe those attractive interactions, they change the critical properties. When you're really close to the transition, they change the behavior in a big way. But maybe things like the very high density of low frequency modes survive even though the critical point is different. So again, let me say, the thing that's in these slides, I'm going to call this the Boson Peak. You remember in jamming in Pier Francesco's lectures, there was this I think they called it d of omega, and this d is, of course, not the dimension of space and not the dynamical matrix. This is the density, sorry, this is not the, this is the density of frequencies which did this. And as you got closer to jamming, it looked constant. That's a weird feature that's shared with our mean field theory of jamming. And then I have to explain what the Boson peak is, and this is going to be a little obscure. If you plot the specific heat I'll call it specific heat, as a function of temperature. It looks linear at first, and then it looks, let's do log. Then there's a region which looks linear, and there's a region that looks cubic. So this is T, and this is T cubed, while the crystal just looks like T cubed, right? Crystal looks like T cubed, and a glass always has this T. And this is something that Cornell is famous for. The master's student working with Bobby Pohl around the same time Ken Wilson was doing his normalization group measured this in a very cool set of experiments for lots of different glasses, and they always saw T. And these were the tunneling center theory of glasses, which were part of the Lesouche notes that Phil Anderson was talking about. Anyway, if you now plot the specific heat over the crystal specific heat that you would expect from the elastic constants of the glass, you got this linear part, and then you got this bump. So you had more specific heat in this temperature range than you would in the crystal. And this was attributed to extra low-frequency modes because it's a glass. And endless numbers of papers, including ones of mine, tried to discuss this bump. This is called the Boson Peak. I'm doing a good job of filling time so that I don't run out of slides. That's called the Boson Peak, and the Boson Peak is, roughly speaking, these extra modes. That in the glass, you would have d over omega that looked like omega, I think, cubed. I'm happy to be told it's squared. It's squared, thank you. Good.
Jim, I have a question.
Yeah.
When you say our theory, are you in the lattice? Because you said that P is probability of taking out some links.
Say your question again.
Is the theory that you mentioned?
Yes.
That with these predictions, is this on the lattice?
So the theory we're building on, but we're not going to do today, tomorrow, is this lattice.
Okay.
Okay? This is the one that our predecessors in this field, Danilo and Mao and Lewinsky and Stendhal, they studied this. They found a jamming transition. P was the probability. There are two P's. There's a if you look hard, you can see kind of hexagons here.
Right. Yes.
And those hexagons have short bonds. And one of the P's will be the short bond, and the other P will be the longer bonds making triangles. Yeah. And they've developed the whole theory in terms of those P's. And when we decided to try to simplify the theory, which I'll tell you about, we just left those P's in. And our theory has no, I'm sorry, Danilo has a derivation of the theory that I was hoping to understand well enough to talk about, and I'm not going to do that. I'm just going to write down a theory with some P's in it. But P's you can think of as being like percolation, and there's a jamming part of the P, and there's a rigidity percolation part of the P. And it's just like this. It's the probability of removing a lattice bond, except we won't have a lattice. Good questions. Yeah?
Does this feature in this specific heat happens close to the critical point or not?
This is an experiment. Lots of experiments of glasses all show this. People then start trying to describe it. If you take a jammed system these days and compute the specific heat from the linear response, you won't see the tunneling centers because there's no quantum mechanics inside the simulations of jammed systems. But you will see lots of phonons here. And if you had a density of states that was constant all the way to the jamming point, this boson peak would get to lower and lower frequencies. So I'm not actually sure, I'm sure somebody's done the calculation in this room, whether this becomes a power law, whether at the jamming point you violate some thermodynamic bounds, I don't know. You can't have too much specific heat at low temperatures because then the entropy can go to minus infinity, never mind. Anyway, it's a classical system, yeah.
So there was a paper where they did some quantum computation for jamming. And of course, I mean, jamming is not very well defined when you put H bar positive just because it violates Heisenberg principle. But there is a regime in which you can just do some semi-classical computation and just using the d of omega. And if you just use the d of omega that is
Constant?
you just get t. So
You just get T?
yeah.
It's not extra T cubed, it's just T everywhere. All right, that's cool. So that would be something.
Then when you increase t, then you need to move away from the jamming line. So
Yep, okay.
but really close to jamming, I mean, in a region that scales with h bar, you can get t. But this is just
But this would be a different T, okay? So this T, when you go away from jamming, the low frequency part will become T cubed.
yeah, exactly. So it's
Okay, so that's not the same as the real glasses where this is quantum tunneling. And this is phonons plus extra. So this extra bump is coming from the T part of this curve, something, something, something. Okay. So there's a real hope and belief that these theories are a practical tool to study glasses, even though we're not getting the details of the transition right. Now, I'm not guaranteeing you, I have this feeling, does the viscosity diverge in the Gardner phase?
so maybe I will comment at the end of the
Yeah.
So what we did is that we computed the moduli across the glass phase, and then what happens is that when you cross this Gardner transition, they stay finite. But what you can do is that, so if you take a glass and it's very big, and as you say, these elastic moduli, they concentrate. So if you take two different pieces of glass, more or less you get the same value. But then what you can do is that you can look at the fluctuations. So you take two different glasses, and then you look at the difference between their shear moduli. And this difference is small. It scales like 1 over root of the volume of the system. So in the infinite system size, they are essentially the same. But then you can put a lens, and then just rescale everything with the root of the volume. And then you can look at the fluctuations, the rescale fluctuations. And when you hit this guardian point, you start to see that these fluctuations diverge. And what does it mean? It means that if you look at the fine structure of the elastic moduli, you start to see avalanches. So the divergence of the fluctuations of elastic moduli is just a sign of avalanches. It's just that if you take a very big piece of glass, I mean, it's the fluctuations of these things and avalanches are suppressed like 1 over some power of the volume. But if you just look a bit more careful to that, you can.
That's very interesting. So the question I was asked, the big question that I grew up with was why the viscosity, the time scales grew as an exponential, and although jamming, which is at 0 temperature, doesn't have this, it's possible that at finite temperature, instead of having interactions due to attractive forces, you would have interactions due to thermal fluctuations, and maybe that would make the viscosities diverge in a different way as you approach the transition with lowering the temperature.
Yeah, I mean, maybe, so the way in which, at least I think about it, is that this divergence of the viscosities happens if you approach the glass transition from the liquid or gas phase if you have an R sphere. But then when you go to jamming, you are out of equilibrium, either because you do some very greedy compression, or you take a glass of R spheres and then you compress it. And when you compress it, since you have a time scale that diverges like this, your compression rate will be certainly faster than any of these time scales, so you go out of equilibrium. So the two divergences, in a certain sense, are not related, because the divergences that you have at jamming is just inside a glass, and you forget about the equilibrium. Instead, this one is really about the equilibrium phase at high temperature or low pressure. So, and you get it. So, I mean, within mean field theory tells you that there is this Kautzmann point where you have this exponential divergence.
Oh, you do?
Yes.
Okay.
Within mean field theory, you have a Kautzmann point.
Okay.
You can have.
So our mean field theory is doing this different protocol where you have no temperature and you're greedy and moving in, and the infinite dimensional mean field theory that we could hope eventually to describe in other ways has a diverging viscosity. That's very nice. Okay. Okay, so the attractive interactions are not big enough. Maybe I should rephrase that and say, actually, it's the finite temperature and the falling out of equilibrium that I've ignored. And real mean field theories in infinite dimensions can include those. And then even without attractive interactions, you can get something that looks right. Okay. How are we doing with time?
20 minutes already?
20 more minutes.
Yes.
So I have a choice. This is the amount I need to talk about today. I could either tell you about, first of all, we're going to take a 5-minute break. And the question is, should we have a 20-minute break and actually have time to get coffee? Or should I start my lecture for Friday, and then you can leave early on Friday when you really want to leave early? I don't know whether I'm the last lecture on Friday.
Let me check.
If I'm the last lecture on Friday,
You are the last lecture in the morning, so you could have a
we could have a bigger lunch.
Yeah.
Would you rather have a longer lunch? Or I'm pretty sure I can do everything on Friday that I have planned. Would you rather have a longer lunch or a longer coffee break, or would you rather hear me talk about normal form theory and avalanches? And you don't have to decide now. Stand up and stretch a little bit, and we'll come back in 3 minutes.
I'm sorry I interrupted. The slide was absolutely correct. The exponents, it's just that.
Not completely correct. There was something else wrong with the slide that I've already forgotten. What was it? Oh, I didn't have P on there. Okay. Yeah, no.
That's fine. The actual diverging length scales for jamming, right? So one that goes as delta P to the 1 power, the other that goes as the typical mean field critical exponent, mu is 1/2. That's why it got me confused. For jam, for the longitudinal one, you're looking at that other special length scale for jam.
There was no deep insight. I looked at the paper and I said, these were for this and these were for that, and I carefully tried to put the right one down. But I'm happy, and it shows it shows that you and Steve are in charge, and I'm just quoting. How did I miss curly P?
What?
Is there?
There should be another line, right?
There should be another line. Oh, geez. Okay.
For the density response.
The density response. Okay. Isn't L the density response?
L is related. There's an extra factor of Q squared.
Fine. Okay.
It's just because it's about gradients of U instead of U itself.
So if you want, just for the record, you can say that I just told you that the slide is the exponents. Just because I created the confusion.
No. Nobody in the audience copied down those exponents. Yeah. Are you? Oh. But in the record, it was pretty clear that there was some question, because Steve said that was right. So I'm sure it's fine. I just wanted to write myself a note, add the density response P, or change curly S. And I'll color that.
Just thought. And I'm getting 1/2 all the time. I keep 1/2 in my mind.
No.
It's
confusing. I always.
Okay, how many people want to get coffee now? How many people would like me to continue with with Friday's lecture, which fits well? 4, 5, 6, 7. Okay, and how many people would like to hear about these weird normal forms? Oh, well, okay. So this is completely optional. You can get your coffee now. It's fine, okay? This is unrelated to anything that you will need to understand but we're very proud of this work, and I'm happy to have a chance to brag about it. So you remember the upper critical dimension was 4 for like the Ising model, and the lower critical dimension was 2, and when we did our normalization group, we always assumed that as you coarse-grained, by dl, everything scaled as 1 plus a constant times dl, either positive constant or negative constant, but they were all scaling as 1 plus a constant times dl. But the renormalization group is a complicated flow, right? Here's a typical renormalization group you might imagine. All these blue curves are wiggling around, and why do you say H grows with just a constant? It's got some nonlinear flow. And T has some nonlinear flow. And the unstable manifold for T is curved. Okay, so the first thing is that if you're close enough to the critical point, you're supposed to be able to ignore all those nonlinearities. Right? You know, you can linearize. We're used to, oh, we're close enough, we can just linearize. Except in the upper critical dimension, there's an irrelevant scaling variable in 5 dimensions whose exponent is negative up there. G had a negative flow direction, and then in 4 dimensions it became 0. Right? And below 4 dimensions, it was relevant. This is the destruction of the mean field fixed point, which then develops an unstable direction towards the Wilson-Fisher fixed point in 3 dimensions. And you can't linearize something that's got a 0 exponent. You need to have the quadratic term or the cubic term or something. Because the flow is not properly described by a whole line of zeros, unless there really is a line of zeros, which happens once in a while. So what do you do? Well, first thing, what do you do here? What is this linearized stuff? I mean, Ken Wilson linearized, and that makes sense. And he knew perfectly well you couldn't linearize in 4 dimensions. But he can linearize in 3 because he had a fixed point with only 2 relevant directions. This is a differential equation. Ken Wilson's insight said, I'm going to turn this complicated fluctuations in all scales into a flow in the space of systems. So this is now a big set of differential equations, and the differential equations people have made some progress. They have a whole organized procedure for saying, well, if all of your exponents are positive, then you can just change coordinates to make them linear. I'm going to tell you it's not quite true, but that's a detail. Okay, so here you have coordinates that are wiggly, and here are the flows that are linear, and you can just change your coordinates to u sub little h and u sub little t to linearize. You knew this. You didn't know you knew it, but you knew it in your heart. Because most of you have heard that the liquid-gas transition as a function of pressure and temperature has the same universal properties, but the jump from gas to liquid below the critical temperature on the phase diagram is a curved line, right? That if I look at temperature and pressure, I'm going to get this wrong, but there's a boiling point and there's a critical endpoint, and this is a curve. First of all, this is not little t, right? That's not right. Little t is constant along this coexistence curve. Below Tc, the nature's view is that this curve is really a straight line, which is the Ising model's line below Tc. So little t is doing this, and little h is doing this. And little t has nonlinear terms, and little h. So the coordinate transformation you need to make sense of the liquid-gas transition using the renormalization group flows of the Ising model takes this, rotates the critical point, and then the nonlinear terms straighten out this coexistence boiling line. Good? You can do the same thing in 4 dimensions. You can coordinate transform the Ising model to get rid of all of the nonlinearities except a few. And then the next question is, what things can you get rid of and what things can't you? So this is a little table that sort of summarizes it. For the 3D Ising model, you can linearize everything. So d anything, d little l is 1 over nu times anything, okay? And you get invariant scaling combinations looking like LT to the nu. So this is the 2-dimensional random field Ising model, the Potts model, here's the 4D Ising model. The 4D Ising model, du by d little l is minus u squared plus du cubed. So first of all, you have to keep the quadratic term, which you kind of knew because the linear term is 0. You're going to keep something. You're going to keep the quadratic term. But the normal form theory we use that we have to use insists that you also have to keep this cubic term. And that leads to a much more rich universal scaling variable that you need for the 4-dimensional scaling collapse. So instead of plotting blah against LT to the nu, you would plot L against blah, 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 where this is the Lambert W function. And as far as we know, we're, I've forgotten. I think we're the first people to do scaling collapses with the right thing, but maybe somebody else knew about the Lambert W function being involved. I'm not sure. And you know, Ising model. You got the 4D Ising model, you need the W. You got the 3D Ising model, linear scaling is good. You got the 2D Ising model, there's a logarithm that comes for sneaky reasons. In the 1-dimensional, 3 out of 4 Ising models, you need one of these funny nonlinear terms. Okay. How am I doing on time? 5 minutes, geez, I'm good. So, I'm going to do a quick calculation, and I don't expect you to follow all the details here, and I'm going to show you plots that we're really proud of. So, this is Laurie and Hayden's work, which Artishman Raju was also a big part of. He's the big part of the previous paper with Lorian and many others. I think you were on that paper too. So the 2-dimensional random field Ising model, the disorder, which is what I've been calling little r, but in the literature it's little w, has a scaling that looks like this. Okay, so this, you know, in general, it's got an infinite number of nonlinear terms, but But you can do a coordinate transformation, which we call tildes, and you can turn, and after the coordinate transformation, you get W tilde squared plus B1 W tilde cubed. Well, wait a second. I didn't get any, I can't cancel that one. You can trust, if I do this coordinate transformation, I can find the new W tilde DL in terms of W, and then I can substitute in, and it works this way. And but the omega tilde to the fourth you can get rid of. Okay, because you can fiddle with the coordinate transformation to cancel everything by making B2 and B1 just the right size. You believe me. You believe me that you can prove to order by order all the way to infinity that you can get rid of all the terms. If you believe those two things, that's the sort of thing physicists believe and mathematicians don't. And the mathematicians are right. The later radius of convergence, you don't know. Anyway, you can make them all go away except for B1. And so this is the normalization group equation. People have known these kinds of things, but they typically didn't realize that this term can't be gotten rid of because they weren't thinking systematically about coordinate transformations. This is a really nice thing we borrow from the mathematicians in dynamical systems. Say again? If you had a W on the right-hand side, then with times a constant, then you can get rid of all the terms. Yeah.
So I'm asking why can you not get rid of, add a mapping which has a translation also in the change of variables?
Oh, you're asking why I don't have a constant here? Yeah. That turns out not to do anything interesting. Yeah. In fact, why don't I have a constant here? It's because this has a different dimension than I can rescale W by a constant and get rid of this term. And I think having a linear term here would just make this term now have a constant in front of it. So if I want to keep the omega W squared term simple and 1, then this is the most general coordinate transformation you want. Lots of details, but okay, so this turns out there's actually also a flow for the avalanche sizes, and you can't get rid of a term that looks like S times W in that. All of these flows involve all combinations. When you do this Taylor series for something like the avalanche size, you get terms including both W and S. And the dust settles the invariant scaling combination for the avalanche size distribution. For avalanches, the scaling variable for them is not S times W to the 1 over sigma, which it would be in 3 dimensions. It becomes, ta-da, S even minus D over W, which is sort of what everyone thought before, but times B plus 1 over W to the B times the fractal dimension minus C. It's cool. That's the cutoff. So I'm now going to talk. Oops. Yeah. So here's the punchline. In 2 dimensions, we never could figure this out. And here are some 2-dimensional avalanches when the disorder is high, when the disorder is lower, when the disorder is lower. And you can see the avalanche size is growing pretty quickly, as you would expect. There's an exponential here. It's not a power law. Previous people would do simulations like this, but on a square lattice. Square lattice, if you zoom in here, these bumpy regions have long facets. They were driving us crazy and everyone else has been suffering from them. And so they would do bigger and bigger simulations where the facets maybe got a little less important, and they would find that they could fit all their data with a power law. So here's a power law fit like the ordinary one, and that green curve is clearly not as good as our blue curve. The problem was you would have one generation of people. We would do 20,000 by 20,000 simulations back in the dark ages. They would do 100,000 by 100,000, 200,000 by 200,000. They would have a small range because the size grew so quickly. They could only do a small range, and they would fit with power laws, and they would get good answers and an RC. And then the next group would do a little better and have a lower RC and a bigger exponent. And these shapes were all awful. They never collapsed. So the first thing that Lorian did was he did it on a random lattice. And that made all the shapes look like one another, and we could now take this raw data. These are the avalanche area fractions. And she could now that they were the same shape, she could collapse them, and the data points showed how much they had to shift the sigma of W to collapse. And then you could fit all the data with our formula. So instead of having a range of 20% in disorder that other people could collapse, we can do a whole decade, a factor of 10. A factor of 10 in disorder is huge. And 4 decades in the sizes. And this simulation is not 20,000 by 20,000 or 100,000 by 100,000. This is a 1,000 by 1,000 simulation. One moral of the story, sometimes, rather than working hard to do the biggest possible thing, if you can do something like a scaling collapse, if you're looking to extrapolate to the thermodynamic limit, doing bigger and bigger simulations may not be the efficient way to go. It may be better to do smaller and smaller ones, because you can get a lot more bang for your buck by doing lots of little simulations and really see what's going on. Thank you.
Is there any question at this point? Okay, so if not, we have almost 30 minutes when we come back at 11:30 for Urbani's lecture, next lecture. And there is breakfast, as you know, above.
So one of our motivations for that was to understand the logarithmic corrections of scaling for jamming.
I remember that.
And it turns out that jamming is...
Wrong things because we have a microphone.
Turns out jamming is, has log corrections that